Well, good morning. Hopefully you can all see the introduction screen. Jay is going to check that for me. Not quite sure why the computer froze, but that's the beauty of live presentation. Again, this is Heinz Knackstedt. I'm hoping the remainder of this will go a bit more smoothly than the very beginning did. A bit of an introduction to C&E sales. You folks are all familiar with C&E, so I'm not going to spend a whole lot of time on that. The shot there that you see there is the staff about 6 months ago in front a little bit of an automatic advance on a couple of the rolls over there. At any rate, again, my apologies for the rough start. Talk about ANSI B1119, which is one of the metal forming standards in the B11 series. It's entitled rather laboriously Performance Requirements for Risk Reduction Measures, Safeguarding, and Other Means of Reducing Risk. With that in mind, here's what we want to work on today. The purpose of the standard, where it sits in the hierarchy of standards. We'll go over some updated definitions because they have changed to some degree, updated and so on. Then I'll review a little bit of the organization of the topics and the clauses. And then I'm going to try to highlight some of the major changes and additions that the 2019 version will have. As Jay indicated, I'm the co-chair of B1119. We update the standard or reconfirm as is every 5 years. And we hope to publish this current revision probably by mid-year. One thing to remember is that this presentation is being prepared before the final document is complete. And we expect some numbers of changes that will come about as time goes on before it is finalized. So what I say here is the current value, but it may be changed to some degree. Okay, organization-wise, the standard is based on the requirement that the decision of what risk reduction measures will be used has already been reached, and you're using B1119 as a tool on the specifics of how the risk reduction measure should be applied. Your requirement would come either from your completed risk assessment or you're implementing a requirement from a machine specific type C based standard. 19 does not specify which risk reduction should be used, does not tell you when a specific reduction measure should be used, nor does it provide any judgment on the absolute value or the application of a given risk reduction measure or safeguarding method for any one specific purpose. The intent of the standard is to inform you on the how to design, construct, install, and operate the risk reduction measure rather than trying to tell you when to use it. The information in 1119 may be used not only in the B11 standard suites, but in other safeguarding and risk reduction standards as well. It is referenced in OSHA, quite often in RIA, and there was a major effort in the standard Z244-1 on hazardous energy, which was put out by the American Society of Safety Professionals, which references B1119 quite a bit. A bit on the hierarchy of the standards. There are A, B, and C type standards. They build on each other. The A type standard is a very generic concept type of standard, talks about how to design a machine safely, risk assessments, risks, hazards, and so on. A type B is a generic standard which covers multiple risk reduction methods, which can be used over a wide variety of machinery. 19 is a type B2 standard in that it gives specific risk reduction devices and methods information. The last type is a type C. A type C provides you specific information on a machine such as mechanical punch press, hot former, or what have you. A change in the way the standard is organized is that in the current version, we have made some changes with regard to how the clauses are organized. In the previous edition, each specific device or method had a complete description of all of its requirement. If this requirement was repeated over a number of different devices, it was listed again and again. This made it more difficult for a user to identify the specific requirements of any one particular type. It also made the updating more difficult for the standards committee. In addition, of course, there would always be references back to other requirements, such as if a device had a muting application, the muting requirements would be an indirect reference within the standard. What has changed is that clauses 6 through 10 have both a general requirements clause and multiple function-specific clauses. That is to say, they give the general requirements for the classification of the other devices in that general clause. In order to understand the application of the specific method that you're looking at, is you need to read both the general and the function specific. It's very important that while you're reading the function specific part, you keep in mind the context of the general requirement clause. There we go. My computer got hung up again. It's probably a little clearer if I can give you a quick look at the table of contents. You see there in the guards section, we have the general requirements on guards, how they're physically constructed, their location, operating and maintenance, and so on. And under there are subclauses which continue to identify the specific requirements for the various types of guards and their specific applications. You see a similar construct under engineering controls, where again in 8.1 and 8.2, the document talks about the general requirements of control functions, and then beyond that in 8.3 and above, the discussion and the definition is for specific function within engineering control function. Home and now a little bit more on the various clauses. Clause 1 is a scope. It talks about the same thing we introduced on how the standard is used, gives some history and so on. Clause 2 is on references. It gives both the normative and the informative standards, which add additional information, either requirement or just general knowledge to the standard that you're reading. Clause 3 is a very important part of the standard. It is the definition. It should be read before going into the standard base. The reason for that is many of the definitions are what we call pro words. They have a very specific meaning as they're used in the standard. It's fundamental to understand the use in the standard, and it does not typically have exactly the same meaning as you might be given in Webster's dictionary. As an example, there are specific requirements and functionalities between individuals, personnel, and operators. And without understanding what those are, the assignment of tasks would be difficult to generalize. The general terms that are used within the standard are defined in B11.0, that A-level standard we talked about. 19 definitions are specific risk reduction measures, terms, and then in a type C standard, you would get the definitions for machine-specific items, such as what is a RAM, what is a slide lock, and so on. If, for example, you were looking at a punch press standard. In order to use this suite of B11s, you really need to have a copy of B11.0, B11.19, and the C standard if it's applicable. You have one for the machine. If you do not have a C type standard, then you would use the result of your risk assessment. We have updated the definitions, some based on need for clarity. For example, we are now using the risk reduction measures term instead of protective measures, just because it's a little bit clearer. And it's also an attempt to harmonize with other standards to use similar terms. We also have a couple new terms that are required in the body of the standard to identify certain functions. We'll begin by using some of these terms in this presentation. As you all know, it's difficult to teach an old guy new tricks, so you will see me retroact and use some of the older terms as well. Generally speaking, in the standard, when we introduce a new term, we include in the definition parenthetically the old term that used to be the same, have the same meaning. Okay, let's go through a couple of the definitions. Excuse me again, I'm getting hoarse here. Engineering controls is basically the entire, encompasses the entire idea of safety controls. It includes the guards or the devices, as well as what we call the SRPCS, the safety-related parts of the control system. Those are the controls that do the actual logic functionality and the monitoring of the inputs and the outputs, and of course are either individually or part of the machine control standard, depending on the safety performance capability of the controller that you're dealing with. And here we are stuck again. Okay, next, engineering controls. These are the requirements or the definitions of just those portions of the safety-related parts of the control system that are being used to reduce the risk. They include such things as the performance of a given safety function, such as how should a protective stop operate, what modes of operation should there be, for example, for a special safe function that allows you to feed wire into a welder with the gate open. We have engineering control guards. Basically, a guard is a barrier that provides some kind of protection from a hazard. It is a physical device, and again, are categorized by their value as to exactly what it is you're trying to get them to accomplish. Shields are typically not considered to be guards, although they are a partial barrier and may also perform some functions that are typically attributed to guards. One way to look at it is that they're defined by their primary purpose. Guard, keep things, specifically individuals, out. Shields keep things like chips, fluids, tools, and so on in. It is, however, true that a guard or a shield may perform also the function of the other. For example, shield over a lathe spinning spindle and the tool contact point does provide partial guarding function from the rotating tool, which is behind the shield. Similarly, on a guard for a welder, although its primary purpose is to keep an individual out of the welder ram, it also prevents and reduces ejection of sparks and radiation as a side product. Okay, then we have the last of the major controls, engineering controls, called devices. Again, as shown in the parens, we used to call those safeguarding devices. They are now listed under engineering control / devices. These are the devices that provide the protection from hazards by preventing or detecting exposure to the hazard zone. They are not physical guards, typically with one exception. These devices do include, but are not necessarily limited to, such things as interlock devices and interlock guards. Here in this case, in an interlock guard, we have a physical barrier which has the requirements of guards in addition to the control requirements for the interlock. One large change is that there used to be a category called complementary equipment. These are devices that were typically used in conjunction with others to augment their functionality. That term has been eliminated, and we now list emergency stop devices as part of engineering control device listing, as well as enabling, even though enabling devices, for example, are used in cooperation or in coordination with other devices such as jog buttons and so on. Risk reduction measures, that's sort of the catch-all of what term that we use. That used to be called protective measures or safeguarding. Again, that's an action or a means used to eliminate hazards and or reduce risks. Rather generic term, the idea is when I introduce a risk reduction measure, I'm trying to reduce risks for a given task or eliminate the hazard altogether. The effort to reduce risks is in a hierarchy listed from the most effective and desirable method down to the least or the less effective method. The most effective method of reducing risk or eliminating hazard, of course, is what we call inherently safe by design. That is that the machine, the system is designed so it does not have any inherent risks attendant to it. After that, we have the engineering control. These are risk reduction measures that are added physically to the main machine, and again, are comprised of guards, control functions, and devices. Last in the list, we have the administrative controls, which are comprised of awareness means, safeguarding methods, information for use, and personal protective equipment. The thing to recognize here, and the reason they're at the bottom of the list, is that they depend on the individual to follow the rules and to correctly apply them. So they are very user sensitive. Moving on in the clause description, clause 4 is a list of responsibility for risk reduction measures for supplier, user, integrator, and personnel. A word of explanation, the user in this case is not the machine operator, but is in fact the entity that is using the piece of equipment to produce the product or the process. Typically, you would call it, might be considered the employer. So that is the organization that is operating the system, but not the operator himself. Clause 5 introduces risk assessment. It primarily points towards the ANSI B11.0, which has the details of risk assessment. Clause 6 is inherently safe by design. 7, 8, 9, and 10 then are the engineering controls we've already discussed, including administrative controls. There are a number of there are a number of annexes within the standard. A number of them have been either added new or a lot more information has been added. Reaching distance consideration for protective devices, we've added some datum that gives you information from anthropomorphic data that says 95% of the population can reach this far over this type of a guard. New information on nip guards, often called also inbound nip guards, where roles have a draw-in risk hazard. There's some additional information on the calculations of safety distances, some additional information on safety distance for engineering control devices. The point here is that the reach over, for example, of a physical guard is different than that of a beam. in that in a physical guard, you can get soft tissue deformation. You can lean into it and squeeze, whereas safety light curtains, when you're there, you're there. Then a bit more clarity on how to calculate primarily stopping performance, how long it takes for a machine to reach a safe condition. And then there's an all new section on safety functions for power drives, which includes such things as safe stop, safe speed, safe torque, those kind of things, which are available in both drives and also as options in the newer robotic controllers. A little bit about the inherently safe design. That basically says the machine is designed so that it is safe, at least for this particular task under consideration. Need to make sure that it is tamper resistant, that an individual cannot remove the design capability. A typical example might be where the pressure available on a clamp is limited by design, and someone goes in and changes the pressure reducing valve, and in that way reduces the safety function by increasing the hazard due to pressure injuries, crushing injuries, that sort of thing. Okay, we have the safe opening safeguarding, where the part actually blocks the opening to the hazard. Safe location, where the hazard is located in a position where it is not accessible. One point to remember is that inherently safe by design does not include the engineering controls as a means of risk reduction, because those are things that we are adding to the machine after the design. The thing to note also is that when there is a failure to danger of one of these risk reduction means, the risk goes back to what it was before that system was installed. A little bit more on guards. Typically, the guard requirement has been you cannot reach the hazard by reaching over, under, around, or through. There are many machine guarding applications that can't meet that level of performance, but still provide some measure of protection from at least inadvertent contact with the hazard, whereas the reach over, under, around, or through is pretty much an attempt to circumvent the guard in many cases. Many C-type standards have requirements for guarding that can't meet that higher level of performance. Such things as grinders and lathes might be a good example. The risk assessment needs to be used to understand what the requirement of the guard will be and which of the normal guard requirements need to be followed or can be done, and so that the guard can be used both effectively and the intended purpose of the guard is there. The most desirable, of course, is to design the guard so that the reach over, under, around, or through is achieved. But again, the task and the purpose of the guard trumps the absolute requirement as it used to be done. Physical barriers are typically categorized as guards, awareness barriers, or shield. One thing that has been cleared up, it comes up quite often in seminars, is movable guards, which are typically hinged. How should they be held closed? If they are held closed with fasteners that require tool to open, i.e. no latches, no thumb screws or wing nuts, they can be considered as a fixed guard, even though there are hinges on it, on the basis that the hinge is there to safely open and gain access to the hazard after lockout tagout has been completed and special tools are used to gain access. If that's not the case, then the guard would need to be interlocked. Interlock devices, interlock guards, movable barrier devices, all engineering controls, even though they must also meet some of the physical requirements of fixed guards. Another definition, reach distance, the ability to reach over an obstruction around it or what have you in terms of a physical protective structure. A number of the requirements in the safeguarding methodology requires that such things such as resets not be reachable from inside the safeguarded space. You can use the same data that you use to prevent someone from reaching outside into the safeguarded space to reach a hazard. You can use the same dimensional data in terms of reaching out to a reset, so that if you put the reset button, for example, at that location where it can't be reached, you can use that data. Safety distance is just a generic term that talks about how far away from a hazard does an engineering control device, such as a guarded device, have to be installed so that the individual cannot be exposed to the hazard. Here's an example of some data: the height of the guard fence, the distance horizontally, and the height of the hazard zone. All three of those together determine where the unit can be. If you know either two of the three data points, then you can determine what the third would be. If you know the height of the hazard zone and you know how far the fence is going to be away from it, then you can use this table to see how high that fence has to be. There's also data on reaching into openings with physical restraints and so on, again, to give you an idea of how a guarding system can be designed so that you do not have access to the hazard. The next clause is engineering controls functions. Again, the introduction is on the performance level, what we used to call control reliability. It discusses briefly what occurs to the safety function when there is a failure to danger of one of the components. What are the results on the total safety function? Also talks about the performance of safety-related resets, which are required when full body access to the hazard is available, or there is a need to prevent hazardous situation by controlling when they can be initiated. A new term that has clarified a situation which is quite common in robotic application and cells, known as pass-through. Pass-through is defined as when there's sufficient space on the hazardous side of an engineering control device such that an individual can pass through it and no longer be detected, and the engineering control device can be restored, reestablished, i.e. reset. Used to be known as a pass-through. This may be an opening in a perimeter guard where it's pretty well understood. However, there's also a point where there might be a point of operation where the minimum safety separation distance was such that an individual can pass through, for example, the safety light curtain and stand on the hazardous side of the safety light curtain, and the safety light curtain can be reclosed. Similar, it'd be where an interlock guard can be reclosed with the individual inside. Those are considered full body access and require manual resets with some specific requirements. Obviously, one way to make sure that the hazard is eliminated, risk is brought to a minimum, is to use lockout tagout, but that's not always possible. If lockout tagout isn't practicable, then we go to what we call alternative methods, and that is using engineering controls. And one of the things that we want to do is prevent an individual from being inside the safeguarded space without being seen. We need to either eliminate blind volumes where an individual can't be seen from the outside, or add presence sensing to detection devices, which of course would indicate that there's an individual in there. The manual reset button then is used in conjunction either with single or multiple reset devices so that an individual attempting to do the reset has indeed full visual acuity of the entire safeguarded space and assure that there's no one inside. Obviously, we can also use the presence sensing devices, which would automatically prevent a reset in the control function. And then we can also do what we call inhibit functions. The inhibit function is a way to prevent the machine from being reset, the safety device from being reset. We have what we call proactive. These are actions that we take as we enter the safeguarded space using keys, trap key systems, personal blocking device at the point of entry, such as affixing a lock to the interlock section so that the limit switch can't be re-engaged, those kinds of things, or using a time-limited safety reset enable, which is set when an individual starts to leave the hazardous space, and for only a short period of time can the reset function. We also have what we call the reactive inhibit function. These must be used in conjunction with a preset warning that says that an individual is attempting to reset. This warning then allows an individual inside to take evasive actions, such as operating a maintained off override device, such as a detented push button that is readily available for where these blind spots might be, and is functional override for all modes of operation. In other words, the system can't be restarted. Also, a thing to remember is that there should be an internal release available. Everybody is familiar with locking the, say, the gate using a solenoid lock, but one must also remember that some fastening methods, such as barrel bolts and twist handles, once they are shot, even though the system is not locked per se, may not give access to an individual from the inside. And they would be locked in, or trapped maybe is a better term, and they themselves would not be able to exit the safeguarded space. The initiation warning system, which we use in conjunction with the reactive inhibit function, is such that we generate this warning, and till this warning period has been completed, the safeguarding device or the engineering control device cannot be reset. Reason for this concern is that when the safety-related parts of the control system are reset, such as the safety light curtain has been reset, we're now depending on conventional controls to prevent motion, which is not obviously not safety rated, and therefore there's an increase in a potential risk. Another thing to remember, this reset of the safety device does not initiate a hazardous motion. We also have the possibility of a pre-start warning system, in which case there is a warning before the machine starts to move. This is used most frequently for automatic cycle start or jog. We also have removed a term from the standard. We have taken bypass out because of its negative connotation, and it is, the term now is suspension. And basically what that says is that under the mode of suspension, the safety function is disabled and is not in a position to eliminate the hazard. Other means are called in to use that. These may be initiated either manually using a defined operating mode, such as I indicated before, stringing the arc welding wire where the gate would prevent the ram from moving, but with the manual suspension mode, of that gate interlock allows the feed rolls for the wire, for example, to move. The other one is muting. Muting is done automatically and is called by the safety-related parts of the control system, typically doing a non-hazardous part of the cycle, such as an upstroke, or by implementing some additional risk reduction measures. This is not manual suspension, this is bypassing. Notice here that the individual that did this had some safety training, because this is indeed a dual channel bypassing. A bit about safety distance calculations. There are two distances that need to be considered. One is the distance from the hazard zone that this device must be mounted so that an individual is not exposed to the hazard. This is based on the amount of penetration that an individual can gain before he's detected, and the amount of distance that an individual can travel during the time that it takes from the detection point until the hazard is brought to a safe state. Then there's also the reaching over, around, or through of the control device, such as reaching around between the safety light curtain and a protective structure. The location of the protection device then needs to be mounted at the furthest distance. It is often desirable or necessary to change the sensing field that we use to shut down or provide the protective function, either by modifying the field itself or perhaps by switching between multiple sensing devices. Typically, these are called sensing field switching, which are most predominantly associated with laser scanners or area scanners, and sensing field blanking, which has typically been attributed to safety light curtains and beams. Here's an example where the robot has two working positions, a left and a right, and a transfer position. And what happens here is that the operator can work on the right, the protective field is on the left. As the robot is moved from left to right, the field is active over the entire area, and when the robot is safely docked to the right side, then the right side is monitored and the left is available for an operator. Below there, we see a couple other field changes. A little bit on interlock devices. They are typically attached to something different, although they may be either a mechanical block or they may also be electrical. The most common use is that the interlock device is used along with a movable guard that then enables the control circuit to shut down the hazard if the guard is open. The interlock system may be with or without guard locking, which is an additional electrical system, typically a solenoid, that allows the guard to either be locked or opened when the release signal is received. They're also used on barrier devices. Trap key systems are a methodology by which a given action will provide a key which allows additional function to be taken place. And the great value of this is that one can very easily control the direction in which the operation takes place, the sequence in which they can be done. Additionally, we have such devices as safety mats and bumpers and safety radio frequency devices. We then also have actuating controls, two-hand control devices, single-hand, hold-to-run devices, and enabling devices. Difference between hold-to-run and enabling is the hold-to-run is an operator that will allow the hazard to be initiated while the hold-to-run is being operated. The enabling device is an enabling function which allows other devices to function. A bit of a change in the terminology. Previously, the amount of distance that an individual could reach towards the hazard without being detected was known as DSA-PF, depth of penetration factor, which was derived originally in its use with safety light curtains. There are, however, other items that have a reaching distance. So in this standard, the term has been changed to D sub DS. A typical example for here is a two-hand anti-tie-down scheme with shrouds, and the safety separation distance is based on the stopping time, or the time that it takes for the hazard zone to reach a safe state after the nearest button has been released. The other side on the right, however, does not have any shields, which allows an operator to extend part of his body, such as holding the button down with his elbow and reaching towards the hazard with his hand. Therefore, we have both the D sub DS for the distance that he can get a head start, if you will, and then also the shutdown reaction time. This is a reference to a number of the annexes that we talked about. The equation that we use for the safety calculations, D, the separation distance, is the hand speed constant times the time that it takes for the hazard to reach a safe state, plus the separation distance, the distance that someone could approach the hazard before being detected, and this last term Z, which is typically attributed to scanners, and that is an uncertainty value that is supplied by the manufacturer and is a function of the design of the device. By the way, the hand constant speed K is typically taken at 63 inches per second. So knowing the stopping time or the time to safe, one can calculate what the separation distance needs to be. Additionally, as I indicated, we've now included emergency stop devices with the other, i.e. now called engineering controls. Here's a typical example of where the general clause and then the specific clause comes in very handy. All of these devices, as far as the functionality of the controls goes, the requirement for a detent and so on, are all pretty much common to the e-stop devices. So they're listed in the generic clause. Then the push button functionality, rope pull, or what the physical requirements of each of those devices is listed separately. The generic plus the function specifics together then describe the functionality of that device. In the last clause, clause 10, we have the awareness means. Awareness barriers. Awareness barriers are devices that give you a physical, tactile indication that you're approaching a hazardous zone, but do not prevent you from getting there. Such things as a chain across the front. By the way, a line painted on the floor is not an awareness barrier because it doesn't have that physical impact. It is more an awareness sign. The awareness signals, of course, can be either visual or audible. Again, notice all three of these, effectiveness is a function of the reaction of the individual when they become aware of the situation, either by the barrier, the signal, or the signs. As a last item, we have the information for use, the instruction manual, handbook on how the system should be used, its intended use, and so on. Safe work procedures on how to do the work safely, and then training and inspection and maintenance are in the list as well. Some of the administrative safeguarding methods are require a work method which identifies specifically how and in what locations the work must be accomplished, where the operator must hold the part, where he must stand, and so on, so that while the risk is lowered, it is not completely eliminated if he does not adhere to the methodology that's been laid out. So this is very training sensitive and has to be correctly taught and monitored. There's a new section on supervision on tamper resistance, and what that talks about is not only how to make an adjustment tamper resistant, never talk about tamper proof because that's an impractical goal, but also on the implementation of tamper resistance, such as you don't keep the key in the lock, you don't write the secure password, HMI, what have you, those kinds of things. And there is a short section on control of hazardous energy, pretty well coordinated with the Z244 that we talked about. That was issued just recently by the American Society of Safety Professionals. Note the change in the name, used to be safety engineers. Because of the population of the group, that terminology has been changed to professional. And last but not least is the personal protective equipment, which again is effective only when it is used and used correctly. That is the end of my official presentation. Again, my apology for the technical issue about the computer hanging up. As you all know, live demos are the most risky things that they are. Jay, are you still there? Are there any questions on the system?
I am here. Thank you for your time. Good job. A lot of good information there. We'll give just a few seconds. I don't see any questions at this time. We'll give that just a few moments. Sometimes it takes some time for people to get something typed in there. Okay. I still don't see anything. Everyone, if you're still here, I see some dropping off. If you have any additional questions, feel free to reach out to CNE, either the 1-800 number or Heinz directly, and we will absolutely try to help. Thank you for your time. Everyone have a good day.
Thanks, Jay.